So I keep getting asked if I'm going to say something, and my plan was to say something about Gaussian elimination, but I wasn't going to until next lecture. But I am going to start hinting at it today, or I'm going to try to. Please ask questions, and then I'm also going to keep deferring the grading question. But for people who know, or like Paolo, there are going to be enough hints that you can figure out what's happening with the grading. And so what I want to say at the outset, whether it's shown up yet or not for you, this internal secondary quantum grading, which is there, and I just haven't picked it out. You know, Emmanuel, he won the space race and put the flag on the moon. So he's got the convention that sticks, and unfortunately, mine is going the other direction. So life sucks. But there you go. Otherwise, it really looks like our lectures are perfectly synchronized, as though we talk to each other ahead of time, which, of course, we do all the time. So I do think that there is a lot of value in trying to bounce between the two. Mine is, as Emmanuel has pointed out, trying to build from the ground up, and he is coming from the top down, but there is a lot of overlap in between, particularly on the algebraic niceties, and I want to spend a little bit more time on that today. Okay, questions about this? Is it really 10? Oh, that clock's on. Good. Everybody's happy. Totally delighted. Last time you understood everything? Perfect. Wonderful. Let's carry on. So if T is a tangle, remember these are always four-ended tangles in my case. Then what we'd like to know by analogy from the story I told last time, we'd like to know that the following pair of chain complexes, T and its mutant, so by direct analogy with the Kaufman bracket skein module, that these are the same, but what does the same mean? So this is homotopy equivalent as complexes. But of course, where we got to last time was basically this object was desired, and I said what we'd like to do is interpret the single crossing chain complex that has the two resolutions in it we'd like to interpret that as a chain complex. But really, I have to answer the question, what is this thing? Because so far it's just a bunch of symbols and something rather hopeful. Okay, so for people that work through the exercise, there is hope that you get a chain homotopy equivalence associated with the Reidemeister 1 move, and that's actually what's going on. But to do anything with higher number of crossing, I have to tell you what this gadget is. So in words, so T is so the answer is that it is a chain complex over the category Cobb mod L. So what this means is that in symbols, this double bracket lives in, well, Cobb mod L, which I'll remind you is a k-linear category. And I have to build that out a little bit by taking something called the matrix closure. And then once I've done that, I can study, and now I'll again defer to Emmanuel's notation because he got there first, take complexes modulo homotopy, and that is the sense in which these are chain complexes. Okay, so in this world, you really can interpret these pictures as complexes. And what does that mean? Okay, so remember, this is from last time. This is our k-linear category. We mod it out by certain relations. So we cut down the morphism size by doing things like setting the sphere equals to 0, and then we played around a lot with this 4-tube relation. So last time, this is a k-linear category. Also known as a pre-additive category. The matrix closure is sometimes called the additive closure of a category. Category theory, as far as I can tell, has at least 2 names for every single thing. So the matrix closure, so once you do this, now linear combinations of objects make sense. Here is linear combinations of morphisms that made sense, right? So linear combinations of morphisms are allowed. And that means that in order to make sense of morphisms, I need whole matrices of morphisms. Between them. And here I'm taking chain complexes of objects in this new category, matrix closure of Cobb mod L up to homotopy. Yep. Yeah, now. Okay, finish the question. Good? Yeah, so I'm taking a cohomological convention to follow the, now I'm going to build one of these in an example. No, linear combination of the morphisms were allowed. Now, sorry, linear. I said objects, but I wrote morphisms. Thank you, Paolo. That's the problem. I was trying to walk and chew gum. So yeah, you're allowed. This is k-linear means linear combinations of morphisms are built in here, and this is linear combinations of objects. And in order to do that, and that means this is exactly what Emmanuel was doing in his talk when he was taking these 2 objects that were sitting in the same grade, and he was bundling them together as a direct sum. And then actually his edges could be bundled together into matrices. So let's do this in an example. So great. So last time our example was a single crossing tangle, and now we're going to do a 2 crossing tangle. And OK, so here's the trick. You're going to order the crossing. So let's call this from left to right for convenience. So this is the first crossing, and the second crossing. So if we think about applying Kaufman's rules at every single crossing, so for a given crossing, I get a pair of diagrams with 1 fewer crossing. And so if I apply that rule at every single crossing, I'm going to get 4 different diagrams. And Kaufman's state sum formula tells you how to put those on the vertices of a cube. So we'll do that now. So the vertices of the cube look like if I take the pair of horizontal resolutions, those are the 1 resolutions. Maybe I'll put a little cheat sheet right here. So I can resolve this by the 0 resolution or by the 1 resolution. And the 0 resolution is this one, and the 1 resolution is that one. And that's going to allow me to put these at the vertices of an honest square in this case. So the first resolution has that's the 0, 0 resolution. right? So I've taken 0 in each location. So given a pair of zero, like a string of zeros and ones, I can go in and follow the order and just apply the rule at each of those crossings. So I can go, this is what I was saying in words last time, I can move back and forth between my choice of diagram and this cube that has no crossings in it. They're equivalent data, okay? And the trick is to try to interpret the thing you get with the, like the big mess as a chain complex. That's what we're working towards. So I could change the first entry, but not the second, to a 1, 0. And it will look something like that. And then down below, I could do the opposite. This is, it's like taking the, I don't wish I moved this up, but we'll just work with it. And then the last thing is these guys here. Okay. So now what I want to do is orient the edges so that I'm always increasing some entry from 0 to 1. And remember what change is happening using the saddle so that I'm keeping now information not just about the objects, which is what's happening in the Kaufman bracket, but also information about the maps. I want to make a comment since we just keep coming back to it. This gadget right here, if you know, in order to put the gradings back in, does everybody have this written down? I'll be there. If you started with an orientation, which you'd have to in order to make sense of the gradings, or the absolute gradings, I'm going to say something about the relative gradings, then this gadget here becomes, well, that's the one that doesn't obey the orientation, and that's where these zips have been put in. And of course, I've turned my head on my side, and everything goes left to right, but it's consistent with the actions being left and right. So I continue to advocate for this. Okay. All right, now we have to maybe a shorthand for the edges. I'll make them big. So here, I just need to know where the saddle is happening. So I guess I'll change colors so that we don't get these confused with zips. So there's some saddle happening at the first entry to change that from a horizontal to a vertical, and you can draw that as a saddle if you'd like. Here the saddle's happening in the second location, right? It's the second entry that's changing from a 0 to a 1. So you add a little band here to obtain that saddle move. Everywhere else away from the crossing, the cobordism is the identity. Now you have to apply it in the second entry, or the entry you haven't done yet. And now the only difference about running around either side of this cube is that you've just reordered the saddles you've attached, which is just an isotopy of these cobordisms. So I've changed the height that these saddles happen at. So far this square commutes, and I have to sprinkle signs in somewhere. And this should be the same as a manualist convention. But where did this minus sign come from? What I'm doing is, so this is -1 to the, well, let's call this edge something. This edge is what's happening when, so this is 1 and 1. So I'm changing this in the second entry. I'm making a change. And in the first entry, I've already got a 1. So I can just count all of the 1s that I have before the star, and that gives me a convention. So number of 1s before this little star. And that gives me a way to sprinkle signs in. And now the side's anti-commute, and you get something that has a hope of squaring to 0. Now I have to collapse everything down. So here I have something of dimension 1. So here I'll write, this is in homological grading I equals something. So just call it I. And then as Gregor was pointing out, I want this to go upwards. So I plus 1, sorry, and I plus 2. These are homological or cohomological grading. And so far it's just relative grading. And this is coming from the height. You just have to count the number of ones. So there are no ones here. That's in grading I. And there's 1 1 in each of these entries. There's I plus 1 and 2 ones, I plus 2. Okay, so that's how we're deciding the height. So there now, it would be better if the vertex of the cube were down the floor and I've got some hypercube. And then I can actually measure this as height, but that's not how I did it. And then in general, you're expecting a cube. I'm not going to write it down, but the number of vertices of this cube are going to it should be 2 to the number of crossings in the diagram you got. Okay, so this gets big fast. But then what's happening when I try to write this in terms of the matrix closure? Well, I've got some k vector space generated by a single picture. But here I've got a k vector space, and it's generated by a pair of pictures. And then the last one is the k vector space generated by this one last picture here that has the extra closed component. So this is something that makes sense in Cobb and also in Cobb L. So finally, we're seeing the additional objects show up. Right? They didn't show up for the single crossing. And then everywhere else, there's zeros. So that's the thing that's meant to be complex. And then I've got a differential in each of these locations. So this is, according to the conventions I was using yesterday, at the end of yesterday and in tutorial, this is di and di plus 1. So those are superscripts to remind you that those are raising grading. OK, so just now I'll write these as matrices acting on the left. So this should be, and it's the column. So I'll just choose the order here and write this. As first, either I'm doing the saddle on one side or I'm performing the saddle on the other. Right, so that sends me to a linear combination of objects in here, one of these and one of those. Right, so it's the sum of those two objects. And then coming out, you get a row matrix. And there's a minus sign in the first entry coming down from here, and no minus sign in the second entry. And then I'll just put the green traces in to remember where the saddle attachments are happening. OK, now maybe that got a little bit small, but I hope that people can see. So first exercise. Check that d squared is equal to 0. Okay, and here maybe that feels tautological to you if you've been thinking hard about the exercises that Emmanuel has been giving you. But one thing to do here is to be mindful about function composition versus matrix multiplication versus cobordisms. So everything's, we pick some conventions. Everything's meant to run nicely together. Functions are acting as functions on the left. Matrix multiplication is doing the same thing. So this really should be the multiplication of these two matrices, but it makes sense to think about what the entries are telling you to do when you do that because of how we run cobordisms left to right. Okay, so there's maybe really a thing to learn here is what the conventions are telling you. Are there questions? This is one of these chain complexes. Okay? So this is as explicit as I can make it. The key thing is that this, whatever it is, so these linear combinations, they don't live in Cobb L. I need to do this cosmetic, perhaps bulky, but somewhat trivial extension where I allow these linear combinations. And that's fine. That's the only way this makes sense. So I think, I mean, strictly speaking, when you're taking com H of BIM, there's a matrix in front of it, but for obvious reasons, one would like to drop this, okay? Again, this is the same for people who followed Claire lectures closely. She started with a pre-additive category or a linear category and then took the additive closure, okay? So we really, these things really do have high level of intersection, even if the pictures look. All right, questions? Okay, so the problem here is that while you could sit down and try to do it, this is growing really fast, growing like 2 to the number of crossings. Oh. Maybe you do? Yes, you do.
So this this little green thing.
Yeah, which I regret.
It's a certain surface.
Yeah. Yeah.
Right?
Yeah. I'm just.
And so if I compose the upper thing, I see a certain surface.
Uh-huh.
If I compose the lower thing, I see exactly the same surface.
That's right.
So there's really, assuming that the conventions are correct, there's really nothing to check here.
Well, hopefully, but I guess I was getting people to actually multiply the matrices out. No four-tube relation. I'm just using the fact that the cobordisms can be taken up to isotopy, so I can reorder the saddles. So without the minus sign, it's a commutative square. It definitely doesn't have d squared equals 0. I have to sprinkle the minus signs in. Don't need the relations. Yeah, so that's a good point. So to obtain commutativity and anti-commutativity, that really boils down to the underlying category Cobb. It's the homotopy equivalences that require, based on the exercise from Rademeister 1, already for Rademeister 1, all of the relations are in play, all of the mod L relations. But as I was saying to people in tutorial, and maybe I'll repeat it as a philosophy, anything that cuts down the size of the morphism spaces is good news. Right? So when we saw, oh, their closed component that's a sphere, I can make that 0, you should be feeling like that's. The morphism spaces in Cobb are pretty enormous. And they can have all kinds of extra closed components and all kinds of extra handles attached all over the place. So yeah, being able to cut these down is a feature, not a bug. Other questions? Yep. Yeah, actually, maybe to restate your question, there's an additional wrinkle one would have to check. If you want to check invariance, I didn't just choose a diagram. I chose an order on the crossings, and I chose a sign convention. So there's some additional things to check invariance under. Just like when you set up the Jones polynomial, you have to, well, let me not unpack the analogy. I'll start losing time. But yeah, certainly there's additional choices going on here. One has to check these things. Other questions? Yeah. Uh-huh. Uh-huh. Well, by maybe giving them different names, like the column 1, 0 and the column 0, 1, like they're just different. They're different variables. It's formal. Yeah, you need to keep track of the actual diagrams you got so you can remember where to put the saddle. This gets bad quick, even for a 3-crossing example. So yeah, keep holding on. What you can observe that they're the same, and then start to reduce everything, and then forget where to put the saddles in, and all of a sudden lose control of what calculation you were actually trying to do. So it's absolutely formal. And indeed, I'll just repeat, that matrix closure is absolutely a formal thing. That's just the ability to take linear combinations of objects. which is, which was even worse when they were all bimodular. I don't know. This is where it's a really good moment to ask yourself, what do I feel more comfortable with? So it really is the same algebraic gadgets, and then one is trying to make sense of, turn these pictures into complexes, and the other is just working with the algebra. And ultimately, there's no one way is easier. This is sort of a test of how your own brain works. Okay, so what I really need to do is, if this is going to be big, then T mu will be big. It is absolutely not clear that the mutant and a tangle should have chain homotopic complexes. But that's what we'd like to start to see. And so what I need to do is get a better handle on the morphism spaces. So in order to do that, I'm going to take a cue from the mutation lecture. I'm going to start by marking a tangle end. So I'll typically mark the upper left. So I have these 4 endpoints. I'm going to distinguish one of them. Remember that the possible choices are related by mutation. So this isn't a crazy thing to do. And then now I want to add a new formal variable. So here it is. I can apply H. So these sheets, I've picked out some little disk, some region in a complicated cobordism, going to be some component that has a star on it. And I'll just declare that by definition. So H is a handle attachment, and it attaches handle with a sign, funnily enough. So this finds the component that has the star on it. It attaches a handle. These are both, this is a valid cobordism, some handle that's sitting on the star component. I shouldn't have changed the star. Having a minus sign in front of is valid, so that's what H does. Okay. And I also want to add point on cobordisms. And these can move freely on components. So what's that going to mean? So maybe I have part of my cobordism here and another part of my cobordism there, and it can now carry a dot. All right, we have to decide what does that mean in this category. It should be some linear combination of honest cobordisms. So here's the linear combination. So dot just means it's a spoiler. It's a sum of 2 things. So now that I have this distinguished component, so the key thing is I've picked a tangle, so that no matter what cobordism I have, there will be at least one component that hits both endpoints. Sometimes there's more than one, but there's at least one component that carries a star on it of any cobordism. So now I can say, okay, well, from the dot, I can run a tube. From the dot, remove the dot, run a tube from the dot up to the starred component. That's a totally reasonable thing to do. And then I can subtract from that the operation where I look at the starred component and I put a handle on it. Okay, so that's the definition of what it means to be, what dot means. Question or stretching? Stretching. Oh, good. And then, of course, I can rewrite this using H, right? This is tube plus handle on just the, the pair of sheets. Yep.
HF and coordinate.
Yep.
And so we were assuming that the coordinate goes from T to T prime, but the star goes to the star.
No. Well, let's back up. Remember, cobordism, the tangles are they're arbitrary tangles that with 4 endpoints and then as many closed components as I like. Right, so I'm in cob L. So now I'm just looking at a given morphism between two of those things is some cobordism. And I've starred one of the endpoints on my tangle. So that means that there's some sheet in that cobordism carries a star. It's just singled out. Yeah, it's true. Yeah, well, we're gonna fix this once and for we're actually trying to get a handle on the morphism spaces inside cob L. So now all of our tangles have that upper left corner marked. You could worry about dependence on this choice, but every single one has the upper corner marked. So there's.
Somehow the sheet that has the star on it.
Okay.
Does not end. So that's a hypothesis.
You have something that looks like, right? I've drawn this saddle, so let's just draw it again. Here's a morphism. It's running from that object to that object. And now what I've done is I've gone in and I'm going to try and manage these objects and understand these morphism spaces by just adding this star. If you like, that's like singling out this whole edge. But the important thing is it said, okay, this sheet, that component of this map is special. Now, it doesn't matter because that's connected. So there's only one sheet, so it's fine. But you could, for comorphisms, you could, on the other hand, have. Well, let's do it because you had the question. You know the old rule in the lecture theater. One person has the question, and many people might. Okay, so this one here. Now, this is where you've actually got something interesting happening. Right, so the saddles aren't the interesting part, but here, now I've got this distinguished sheet. And this says, so H doesn't know how to act until I've said where to add the handle. That's the crucial thing back here. That matters. It seems like really innocuous, but this is like the key step to trying to figure out what these morphism spaces are. Okay? The star just comes as part of the data now. You could be, if you want to be concerned about this, we're now trying to build up something about marked tangles. We'll worry about how to remove what the issue is with the marking later, but the foreshadowing here is the last lecture. Any given choice of marking is related by one of the 3 mutations. Okay, so I'm really, in a sense, I'm baking the solution into the data right now. So, and I'm just telling you, it's got to get more complicated before it gets better. So now we've got marked tangles, which totally reasonable that people are grumbling. They're grumbling. It was bad enough. Well, I just tell myself it could be a lot worse. It could be bimodules. Just kidding. Those are great too. Okay.
So again, what's the difference from the bottom picture? I see
Because I'm only marking one tangle end. The crucial thing is that a tangle end marked actually singles out a component of a cobordism. The cobordism may only have one component, and it's not going to single out any of the closed components. So you could decide to say that you have like connected and non-connected cobordisms, but that's a little bit difficult because you could have disconnected components. We were trying to so anyway, I didn't want to introduce that kind of language. But the point is, do you have 2 sheets or do you have 1? When you have 2 sheets, it's not clear where to add a handle. That's ultimately why I added the star. Okay? Yeah, what you should do is, exactly. Or, I mean, it's a matter of choice. imagine these things came with a star, and that gave me a choice. I followed the choice. Yes. It is. I mean, it's Barnaton's dot. But this is sort of a longer discussion, but this is just a geometric interpretation of Barnaton's dot. Yes, Gregor.
I'm sorry, but I'm still confused. When you talked about mutation, you said there's a mutation where the star now is at the bottom right.
Mm-hmm.
Now, if I look at the lower picture, is the star at the bottom right, then suddenly I have two components that have the star on them.
No, you're changing the starred component. Can I come back to this question? I mean, this is where I'm trying to get to. I literally, that question is the right question, but I can't answer it for like another 40 minutes. That modulo question. But no, it is clear. This is the top left corner. So don't even worry about the other choices. Pretend mutation doesn't exist. All it exists is marked tangles, and I've marked the upper left now and forever. All tangles have the upper left component marked. Then if you're happy with that, I think your question is the right one. It's not, we got to build up some machinery to answer it. It's exactly what I'm doing, or trying to do. Okay, so great. And then what happens? Oh, okay, great. Now you can do an exercise, which may or may not make things worse. So I have a sheet, and it carries a star, and it carries a dot. Then apply the rules and show that that vanishes. I think I'm going to want to be able to refer to this in a minute. So this definition is important. And the next thing. So there's some new relations in this dotted category. Not a different category. It's just a different organizational principle. So I have a S dot relation. I just realized how bad that notation is, Claudius. It's fine. Life sucks. So that, if you have a sphere dot on it, that's no longer 0. That's 1. The second is this H trading, just call it the H relation. And that's that if you see some sheet and it carries a pair of dots, which isn't apparently disallowed, that's the same as H with a single dot on the same sheet. So I can trade dots for H's. And then the last thing is a relation I'll call the neck cutting relation. So neck for short. And that says if I see just a tube anywhere, I can rewrite that as a linear combination of caps and cups. So there's one cobordism running from the same place, but the dot on one end. I can have a dot on the left-hand side. And then minus H times no dots. Remember, the 4-tube relation relates, maybe it makes sense to have that just to make clear what's going on here. The 4-tube relation relates, it's a linear combination of a pair of things is equal to a linear combination of another pair of things. That is to say, there's a linear combination of 4 things that's equal to 0. So here's 4 things equal to 0. This should follow from 4-tube. Okay, so the exercise is to use this new definition star, which has in it a second definition involving what H means, to deduce these 3 new relations. Keep in mind, you can rewrite everything without dots and H's. Right? You can write everything just as linear combinations, but the point is that more linear combinations have entered the room. Right? This object makes sense in Cobb and in Cobb mod L. Okay? And we're just giving things names. This makes sense in Cobb mod L. I can put a minus sign in front of a handle. We're giving that a name. Okay, so we're just trying to make our lives easier. We haven't really changed the category. Yep. No, I'm over a field K. Yep. I can't remove that requirement. Well, here it works over Z. So you can work over arbitrary R if you want, but what's the H of these two disks? Yeah, so that's like the starred component is over here. Right? You should imagine these are like the most horrible surface you ever saw. And that's happening somewhere in the cobordism, and over here is a starred component, and that H says add a handle over here, and you get to get rid of the minus sign. But that's all you know. The key thing is you don't know where to put that handle if you don't have a starred. Okay, other questions? Okay, so now to do those, so now we want to remove closed components. So now, this is what Barenton calls delooping. Well, now somewhere in the cobordism, or somewhere I've got, there's some closed component. There's the elements that are hitting the boundary as well, but that's not, we don't know how to get rid of those. I'd like to remove this, but to remove it, I need a pair of empty sets. And now, which one did I decide to use? So I can cap. That's a perfectly good cobordism that eliminates a circle. And equivalently, another way to remove one of these is to take dot and then subtract off H times the cap. Still on. That's a way to remove things, but this is actually, I can remove them by chain isomorphism. And so the claim is that this is chain isomorphism. So I can have a dot here, or I could close this off with just a regular cup. Okay, so this is now, yep. This star, well, because, I mean, this may or may not have a star on it, on this component. So let's go back in here. Maybe this one had an open component. It needn't be marked. I mean, it can't have the star. I mean, okay, to have a star on it, this would have to be merged into the starred component somewhere else in the cobordism. These are local pictures. Just like this is a local picture, it's some part of some component of a cobordism just clipped out a disk-sized piece. This is just some tube, some macro noodle, and somewhere in the cobordism. Okay. You need the star. So it depends. Like either, you know, in this case, this says cut this, put a dot, add it to cut that, put a dot on the other side, and then subtract off a handle here. Or add a handle there. Okay? Great. All right, so maybe for example, because this is an example that we did.
What was the claim about the star?
Which one, this one here? Well, I'm about to explain it, but what it does is it gives you a chain isomorphism between a complex that has this closed component in it, say something like maybe one of these morphisms, and it tells you how to remove the circle here, and it's going to remove that circle by precomposing with these. So those are cobordisms that go from that closed circle, and they cap them off to give you empty sets on that part of the object. I think an example is going to help for me, because it's the example from yesterday. So now there's a star upper left, and I've got this one crossing tangle, which is a thing that we started messing around with. What is that? So it's this guy here, and so mark star. Remember, that's the 0 resolution. This is the 1 resolution. This is compatible with having this be homological grading I up to some shift, and this being homological grading I plus 1. We can normalize that, but we needn't for now. I'm going to have this. Again, I'm going to mark things. And then let me be very careful about the cobordism. So the cobordism looks like this. Right, there's my 2 vertical sheets, and this is marked up here. Right, so that means that this whole component carries a star. So here we're in an example where I've got 2 components and there's a star component, and it's different than this situation back here, right? Because now if I apply this neck relation, then add the handle really might as well just add the handle onto the original neck. It doesn't do very much. Okay, so I forget what the question came from right here. It does something different depending on the full cobordism. Right? Everything over on the left of the board are local pictures. Okay, so that's where we were yesterday. And we showed that's chain homotopy equivalent to just the 2 vertical, like the no crossing diagram, removes that Rademeister 1. And now, well, how could I remove this? So I claim that this is, according to this diagram, this is isomorphic to, well, there should be 2 copies of this, but without that loop. I'm not doing anything over here. Okay. And now I have to get into this so I can apply that. So I have to get in along here to where the loop is from the empty sets and then apply this thing. Let me draw those explicitly. So that looks like from the top one, there's going to be a dot. So this looks like stars going here. I've now, okay, to try and make it look like the time happened in the right way. Okay, that's this map, but there's a dot on it, right? So if there's a dot on that, there's a dot on this starred component. So then if you did this exercise over here, that is equal to 0. Try to use a different color so you can see it, okay? But then down below, this one here does the same thing. It caps but with no dot. Okay, that cap now is, that's just the identity. Okay, so what this has done is it's changed this into this complex, and really I put a 0 on this component and a 1 on that component. You can recheck. Now this is really starting to dance between the way that Emmanuel was doing Rademeister 1 and the way I tried to understand Rademeister 1. We can redo that chain homotopy equivalence for a Rademeister 1 move, but try to do it using the tools from Emmanuel's lecture. So you can instead take this new diagram, and I claim that this really is in quantum grading shifted up by 1 and quantum grading shifted down by 1 if you want to be punctual about gradings. And everything is in terms of this vertical tangle. And this really is, I mean, I wrote it as 1. Like the identity morphism here, and there's a 0 morphism between the other 2. So that's all of the data. And I guess, well, last time I told you this is in homological grading 0 and homological grading 1, but maybe it's I and I plus 1. And so you could try and show, so reprove, that that's just homotopy equivalent to that chain complex. Now we've got an honest subcomplex that's contractible that we'd like to kill. Okay, so it's the same deal, just in the language of this, in the language that Emmanuel was introducing. Maybe it's worthwhile checking some parts of this isomorphism. So, for instance, if I'll leave some of it as an exercise, but so why? An isomorphism of complexes. I think that's not giving me enough space. So, well, we had something like this. Okay, so this is just the identity. No delooping happened here. These are just the differentials. Those are the saddles. And then what I did was say, okay, I can cap that off to get into empty sets, but the claim is that if I compose that with the other side, I should get back to where I started. So along the top, that's capping things off to get rid of this, but then including things back in with a dot. But along the bottom, I get two terms. I get, so I'm capping things off to get the closing things up with the cap. I did this backwards. Hold on. So bottom, this component followed by that one. So I'm composing the morphisms now. And it's subtracted from h times backwards. Apologies. Okay, so this is one term from along the top. Composing, and this is two terms from along the bottom. And this is cooked up because I've used the neck cutting relation to take this honest identity and just divide it into three pieces. This by the net cutting relation is just equal to that. So this is a question of going back the other way. You've got linear combinations of three things, and they can, I guess there should have been a plus right there. Linear combinations of three things getting replaced by single things. Right, so the statement is, if I've got a trivial cobordism here, write it in terms of these pieces, and those are the pieces that are being divided up into their parts to factor them through empty sets. And so this is factoring through a pair of these gadgets here. Okay. Oh, I'm trying to check that this information, I'm going back to Gregor's question, actually. So I'm claiming that this recipe gives you a way to remove loops, but actually it's a way to remove loops by a chain, like a chain isomorphism. So it's better than a homotopy equivalent. So I'm going from, so it means the conclusion is that my apparently complicated diagrams, I can start to simplify them by, say, moving this circle, which is exactly what we were doing this morning in Emmanuel's talk, which is taking those composites of the module associated with sigma I, composed with the module associated with sigma I minus 1. There was this big complicated diagram. We wanted to start cutting things down. So this is an alternate way of dealing with these objects to try and reduce them. I'm trying to make the complexes feel smaller and be more manageable. But the upshot is that we've done it by a chain isomorphism, not just by some complicated homotopy equivalence. And there's more to check. Yes, Gregor. So by checking the rest, I mean the other composite, which is really two composites.
Yeah, I'm sorry, but I was just talking something. In next relation,
Yep.
is that supposed to be minus 2h? Because I'm looking at the left of that dot operation you just defined,
Mm-hmm.
and I'm thinking to myself, from each of those dots, there appears 1h. So
No.
I may be just confused. I don't know.
They're just different relations. I mean, it'll be less confusing if you do the exercise. And I recommend starting with the first one. It's like the easy warm up.
The only reason I'm confused is because they'll define the dot relation there,
Uh-huh.
and I think from each one there appears, oops, there appears 1h from each of these first two.
Yeah, but you don't know that these are on the same component of a cobordism. Or like I've taken, like if this is the connected tube, then these now sit on different components of a cobordism, right? Because I'm gonna cut this right in the middle. Yeah, Gregor.
I just wanted to say, can I do I understand correctly that this thing up there is a composition of two more components? One is from a circle to direct sum of two empty sets,
Mm-hmm.
and the other one is a morphism of direct sum of two empty sets to a circle.
Yes.
And the composition, because of this relation,
Uh-huh.
is the identity,
In one direction,
and the composition in the other direction is also the identity.
because of the S dot relation.
Or is it not?
Yes, it is.
We are really saying the circle is isomorphic in the conformity
Pair of
direct sum of two empty sets.
that are secretly shifted by quantum grading that I've only done suggestively by putting one up and one down. But yes,
So that's really,
that's the meaning.
and so
And this is it in action, right? Here, this is annoying. It's got this extra close component because that's how big the category is. But now I've written things that look an awful lot more like they're in this preferred basis for describing the skein module. That's what I'm trying to do, right? Like in the skein module, we have this loop relation that says anytime we have a loop, I can get rid of it. I just have to multiply by minus a to the minus 2 minus a squared, and we're good to go. We just carry on with the linear algebra. The problem is here we have to do that, but at the level of complexes. So every time we try to do something that feels like the right brain dead thing to do, we have to do it up to homotopy. The nice thing here is it's happening up to chain isomorphism. Yes, Pamela? Yeah, this is a chain complex. Remember that now this, secretly this is a sum, and there's a 0 coming in here, and a 0 out, and this chain complex is that chain complex, and this is sitting in I equals 0. So it really should look familiar to last time. The only thing that's changed from what we did last time is we've replaced the single gadget that had, last time we saw this. On rerunning the exercise, you see this setup. Now I've kicked Gaussian elimination downfield, but the tools have all been handed to you in Emmanuel's lecture. Does that make sense? All right. Rolling deep onto the second page. Yeah. Yeah, go. Mm-hmm. Uh-huh. Uh-huh. Yeah. Yeah, and in fact, there's wonderfully said, I would love a show of hands to know who that was useful to. It's like exactly Emmanuel, me, and Claudius. But it is true that I think it's only like just saying that without the idempotent language. The net cutting relation allows me to write this into 3 things, and now I could wonder these things. And then I could decide whether or not to put these as a sum along one edge or put these as a sum along another edge. And actually, there's a second version of this delooping that's homotopic to the one I gave you, and it just sprinkles those operations around in different places, but I was trying to avoid that. So there's an additional choice built in there once you see that, oh, this is my option. This is what I'm going to have to work with. All right. So although this doesn't feel, or I'm not getting the sense that this feels like the level of jubilance I was expecting, this is fantastic news. So we've really made things a lot smaller for some notion of small in scare quotes. So the upshot is that up to chain isomorphism, we can re-express any given tangle complex in terms of these objects. I guess it's important that they be starred. Well, the star only matters on the morphism, but let's be careful. So I can get rid of all of the loops that I see everywhere. Okay, so the category got, this things got more manageable. I'm reducing my attention to the subcategory in Cobb mod L that's just generated by these two fundamental basis elements as a subcategory inside Cobb L. Said another way, we've got this category really boils down to understanding two objects, how I pass between them. So I can run this way by a saddle. I can run the other way by the other saddle. Remember, so that should have this picture at the left-hand input. It's a little bit confusing, but that's just how it. Right, so I've got saddles running in each direction. And then I've got this more subtle operation that, of course, it's a category, so there's identities on these. But there's also identity sheets with dots. So this looks like this thing here. And there's a dot. But that would be 0 if I put that on the starred component. So now it's important that I remember where the stars are. And similarly, I've got this identity sheet here. I'm going to try to carefully draw this as a trough so that it's distinguished from these pictures that are, local, these sheets that are just some part of a cobordism clipped out. This has a star in the top left. So just distinguishing everything with a star in the top left. And it can carry a dot down here. So there's the identity morphism. There's just two sheets. And then there's the identity morphism with a dot on the non-starred component. OK, that's basically like the whole show. But of course, I could start composing these. And you could wonder what's going on here. So let's say this in algebra now. Great. So now I want to introduce a name, the Barnatine algebra. I'll use one of the B's that hasn't been used yet, using a quiver. And these are exactly the types of algebra that we were working with last week in Claire Amio's lecture. So here, there's a different kind of dot. It's a dot on a blackboard, not on a sheet of a cobordism. And then there's a D. I'm going to be, it's a D. I'm not going to label these yet. We'll decide how to label them in a minute. S, and there's an S, and there's a D. And we already decided that if I compose a saddle with a dot, that's going to move the dot onto the starred component, right? So in fact, it's a quiver with relations. If I compose first do dot and then do saddle, sometimes that composition won't make sense and then it's just 0 anyway. But when it does make sense, you've got a dot and then the saddle immediately connects the two components and that has to kill the cobordism. So that's 0, as is D times S. Now I haven't, like there's really two different D's, right? There's the D that acts on this object, which is one of my two idempotents in the algebra. And there's a D that acts on the other object, which is one of the other two algebra elements. But I'm not going to single them out. And this is where I realize there's a conflict of, and there's, I mean, never mind. Stop muttering to yourself, Liam. So that's the quiver that's in play. And that quiver, this algebra, is just describing this endomorphism category that's a full subcategory of Cobb mod L. Yep.
Can you say once more why there has to be a dot on this other sheet?
I'm not saying there has to be. I'm saying that is one of the interesting morphisms in this category. There's certainly the identity morphism. Right? I always have the identity that's just a pair of sheets running along. But this cobordism matters. And I haven't, so far it's just one of the interesting cobordisms that I'd prefer not to forget based on how I've set it up. But at this point, now this is, you remark, this is K plus K algebra. I have a couple of copies of K here, one for each of the idempotents. This is where K plus K is agreeing with the subset of idempotents inside these. This is the idempotents. Okay, so now what I want. So what's the quiver telling you you're allowed to do? If I happen to be sitting at this object, there are dot morphisms that lead that object. And in fact, there's dot, composed with dot, composed with dot, composed with dot. So there's many, many composites of dot leaving from this object. That's perfectly legal in the algebra. But I've got a dot trading rule. So every time I add a dot, I can trade it with a handle H. Operator is really going to save us now. Same thing with the S. I can do S squared to come back, or S to the fourth, S to the sixth. There are lots of morphisms in here. It's not until I compose with an S with a D that I get 0. But think about what S squared does. It builds a tube. So you have the net cutter that allows you to get rid of that tube. So you really can start reducing things. And the exercise, I want you to show that this is, show that the morphism spaces, right? So the morphisms from this object to this object, the morphism from this object to that object. There's 4 different jobs to do here. So the morphisms are finitely generated. Over, and this is, you've got this K, and now you've got this third instance of a capital letter acting as a variable, and this is the operator that tells you to add a handle. So it's not a finite dimensional morphism space, but with this magical extra H, you get finite morphism spaces. This is a very manageable algebra, and it's absolutely the kind of algebra that's showing up in Anyo's setup. Yep. Go first. Between, oh, so let's do so s squared, say on this one, let's be careful with it. So s squared on, I don't need that, but on this object, that's this thing here, right? So that's, first do s, and then do another s. Right, so I've got to go over here and then come back. And now here's a tube that I've added. When I compose those together, I can rewrite that in a number of ways. But that's now just a tube from one sheet to the starred component. Agreed? So there's some things, if you haven't seen this before, this has content. Once you've played with it, it feels like it's tautological. I'm not trying to claim that it's obvious. This is where I want this is the sandbox for the day. And I did add the relation on the quiver. I mean, I claim it was forced on me if I wanted this algebra to be this, like exactly this endomorphism subcategory. Yeah. No, I don't need to because it's already in the it's already in the category. Like it's part of the data now. Like I've already introduced it here. So the Emmanuel's question is like, well, when is this happening? But what you can do is you can now rewrite some of these operations. Like what does handle do? Well, handle, which is something I can apply to an identity cobordism, say, is the same thing as s squared minus d. So I can start rewriting. That means I can write s squared in terms of, oh, I got the sign wrong, didn't I? Because I was working in my head. Okay, with no warranty on the signs, right? I can start to reduce things by linear combinations. But that's all forced on me. This is a statement about the relationship to the category. Yeah, great question. Yeah. Yeah. Mm-hmm. Well, I've only got 90 minutes, Gregor. But you're going to prove it by working through the exercise, partly. Okay. So just like in Emmanuel's talk, I can't write everything down. So what actually happened? Now let's kick any discussion of type D structures downfield. And I'm going to come back to your previous question, Gregor, about this star business, because it should feel like an uncomfortable choice. Okay, so this is an orange star. I think this should now a priori completely change how I'm re-expressing my linear combinations and morphisms. It's could change, put signs in all kinds of places. It could completely destroy things. It should still work, but let's see what's going on. Well, first of all, The S operations are not affected. These only have one component to put a star on. Right, so if I go back in here to a saddle, say, and if I move that star to the lower right, that's just like moving the star down around through that component. And the only thing I was using the star for was to indicate a particular component anyway. So the S relations are the same regardless of what happens with star. It's the dot relations that are a nuisance. And so apply A leftmost idempotent. Okay? So the dot morphism on this object, what is that thing? That is so that has a star upper left, and it has a tube. Right, and then I removed it, so then it's handle attachment. Where I've added a handle up top. Okay, so that's what the dot morphism is. So I've removed a step. The morphism really is a pair of horizontal sheets with a dot on this component, but that's a linear combination where I have a tube, either a tube running to the marked component or a handle. Okay, now I'm going to go back to my formalism. This has a tube running and then two caps that I could imagine being there, but I don't see them. So that's one of the players in a four-tube relation. This one with a minus sign has a handle joined up on the top sheet. So there's a minus sign there, so I'm imagining throwing that side and joining it with its friend. And this one would now catch a minus sign. Okay, so now here I'm applying four tube. Okay, now let me rewrite everything in terms of the star. So now this has a handle on the bottom. And minus another tube. So I've rolled the minus sign around here. This looks like I claim this is the same thing as having minus. Well, what if I put the sign down here, or the star down on the bottom? Okay, so four tubes tells you that moving the star from upper left to bottom left on this particular morphism adds a minus sign. This is bad news. It gets worse too, because also if you run the same and you look at this guy here, right? So the dot running from the other idempotent, so I have two of these. Well, if I move the star top to bottom on the left, this actually doesn't change. So that's basically the worst case scenario, I think, that you have a, not only do you have a sign change, but you have an inconsistent sign change. What's that? Oh, yeah, okay, well, but, which is tautologically true, but this is actually, this one is a tautological check. It's just running along the same component anyway. Okay, so this is the bad news. So if you change the star from upper left to lower left, then you have to introduce minuses, well, just on the left-hand D, and then you can rewrite all your morphism spaces. That's bad news if you want to work with sign, but it's the only thing that, so it does tell you something without sign. So I think this is where we're going to get to. The upshot is that if K is replaced by the field of two element, so that signs don't appear, well, what this tells you is that it doesn't matter which endpoint you choose. So that's the same thing, for instance, as marking the lower, oops, I buried the lead there. And this is the same thing as studying T. If I want to move that back upstairs, this is a mutant of T. So I'll write that at C mu, and then so that you can see it at the back, this is where we use mu x mutation. You can check how the signs work. For mu z and mu y as well. This is by picking other endpoints. Well, what we've really learned is that these objects now, they are mutation invariant to a certain degree. Well, they're mutation invariant up to sign, and it comes down to trying to understand these morphism spaces by carefully fixing an endpoint. Now, of course, how does this fit back into things? That's for next time. We should talk about how to reassemble, just like we had from Conway. So in the sense of Conway, we should look at reassembly. But this is at least a mod 2 version of the statement I gave for the Kaufman bracket Skane module for mutation. And it tells you that if you want to understand mutation in general, then you need some means of managing signs. Okay, stop there.